Everyone knows steam engines conquered the surface world. Railways, factories, ships. But almost nobody realizes that deep beneath Queensland's coalfields, a steam engine did what miners swore was impossible. It worked underground. Not just worked, it thrived. For decades, engineers had dismissed the idea. Too much heat, too much smoke, not enough ventilation. The physics seemed impossible. The safety concerns seemed insurmountable. And yet, in the cramped, suffocating tunnels of Queensland's mines, one steam locomotive proved them all wrong. The year was 1887. Queensland's coal industry was booming, but underground haulage was still brutally primitive. Horses and mules dragged coal trams through the dark. Men pushed hand carts until their backs gave out. The deeper the mines went, the more desperate the need for mechanical power. But steam engines, underground, the very idea was laughable. The problem wasn't just theoretical. Steam locomotives consumed oxygen and produced enormous quantities of smoke, carbon dioxide, and water vapor. In the confined spaces of a mine tunnel, often barely wider than the locomotive itself, these byproducts could turn lethal within minutes. Miners already faced explosive coal dust, unstable roof structures, and the constant threat of gas pockets. Adding a fire-breathing machine to that equation seemed like engineering suicide. But there was another problem, one that haunted mine operators more than safety concerns: money. Every ton of coal that had to be hauled from the working face to the pit bottom by hand or animal power ate into profits. The longer the haul, the worse the economics became. Some Queensland mines stretched kilometers underground, with tunnels branching like tree roots. The cost of moving coal through that maze was staggering. Enter James Garland, a Scottish engineer who had spent 15 years in the coalfields of Newcastle, New South Wales. Garland had watched mines grow deeper and more complex, and he'd seen firsthand how haulage costs could strangle even the richest coal seams. He'd also studied every failed attempt at underground steam locomotion, and there had been many. Most had ended in disaster. Smoke-filled tunnels, asphyxiated workers, boiler explosions in spaces too cramped for escape. But Garland believed the problem wasn't steam power itself. It was how engineers had tried to implement it. Traditional locomotives were designed for surface running, with chimneys that vented exhaust into open air. The underground, that exhaust had nowhere to go. The solution, Garland realized, wasn't to eliminate the exhaust, it was to capture it. He designed something extraordinary, a fireless steam locomotive. Not truly fireless, but close enough. The engine carried no actual fire underground. Instead, it was charged with high-pressure steam at the surface, using a stationary boiler. The locomotive itself was essentially a massive insulated pressure vessel on wheels, a steel bottle containing superheated steam at 150 pounds per square inch. That stored steam would then power the cylinders as the locomotive worked underground, with no combustion, no smoke, no open flame. The miners at Queensland's Walloon Colliery laughed when they first saw it. The thing looked like a pregnant boiler with wheels, squat, ugly, barely 10 feet long. It weighed just over 6 tons when fully charged. Compared to the massive locomotives thundering across the Queensland countryside above, it looked like a toy. How could something so small, something that carried no fire, possibly do the work of horses and men? The skepticism ran deeper than appearance. Miners are practical people, hardened by experience. They'd seen plenty of surface innovations fail underground. The heat was wrong. The humidity was wrong. The confined spaces created problems engineers sitting in drafting rooms could never anticipate. And now some Scottish engineer wanted to roll a bomb, a pressurized steam vessel, into tunnels where one spark could ignite coal dust, where one structural failure could trap dozens of men. Garland knew he had one chance. On a cold morning in June 1887, the locomotive was charged at the surface and carefully lowered down the pit shaft. The test run would be simple. Haul a string of coal trams from the working face to the pit bottom, a distance of about 3/4 of a mile through winding, poorly ventilated tunnels. If the engine ran out of steam halfway, it would prove the critics right. If it filled the tunnel with exhaust, men would die. The crew attached 6 loaded coal trams, each carrying nearly a ton. Total load, about 6 tons, plus the locomotive's own weight. The tunnel roof was so low that a tall man had to crouch. The walls were barely wider than the coal trams themselves. Timber props creaked under the weight of thousands of tons of rock overhead. Lantern light flickered in the still, humid air. Garland opened the throttle. Steam hissed into the cylinders. The driving wheels turned. The locomotive moved forward, not fast, maybe 3 miles per hour, but it moved. The coal trams followed, their iron wheels grinding against the rails laid in the tunnel floor. The sound was deafening in the confined space, a mechanical thunder that echoed off stone walls. What happened next surprised everyone, including Garland. The locomotive didn't just complete the run, it exceeded every expectation. The tunnel remained clear. No smoke, no visible exhaust. The only byproduct was condensed water vapor, which dripped harmlessly onto the tunnel floor. Temperature in the tunnel actually dropped slightly as the engine worked, because the expanding steam absorbed heat from the surrounding air, and the locomotive still had steam pressure left when it reached the pit bottom. The numbers were undeniable. A single locomotive could replace 12 horses and do it faster, cleaner, and safer. Operating costs dropped by nearly 60%. The engine could be recharged in about 10 minutes at the surface and would run for up to 2 hours underground, enough for multiple trips. Maintenance was minimal because there was no fire to damage boiler tubes, no ash to clean out, no coal to shovel. Within months, orders flooded in from mines across Queensland and New South Wales. The design was refined. Second-generation models carried higher steam pressures, up to 200 pounds per square inch, and could haul heavier loads over longer distances. Some could work for 3 hours on a single charge. The insulation improved, keeping the steam hotter longer. Safety valves were redundantly designed to prevent pressure buildup. The emergency bleed systems could dump steam in seconds if needed. But the most remarkable thing wasn't the technology, it was the cultural shift. Miners who had sworn steam would never work underground became the locomotive's fiercest advocates. They'd spent years breathing coal dust behind horses. They'd pushed hand carts until their muscles screamed. The steam engines didn't eliminate the danger of mining, nothing could, but they eliminated one source of suffering. The work became slightly less brutal. Production increased without requiring more human muscle. By 1895, Queensland's underground steam locomotive fleet had grown to over 30 engines. They worked in coal mines, copper mines, even gold mines where ore needed to be hauled from deep underground chambers. Engineers refined the concept further, experimenting with different boiler configurations, improved insulation materials, and more efficient cylinder designs. Some locomotives could carry enough steam to work an entire shift. Others were fitted with small auxiliary tanks that could be swapped out underground, extending their operational range even further. Yet despite their success, these engines remain almost unknown today. Ask most railway enthusiasts about Queensland's locomotive history, and they'll talk about the Queensland Railway's magnificent main-line engines, the massive articulated locomotives that hauled sugarcane, the sleek passenger expresses. Almost none will mention the stubby underground steamers that revolutionized mining operations. Why? Partly because they worked in darkness. Surface locomotives were public spectacles, smoke and noise and polished brass. In underground, locomotives did their work where almost nobody could see them. No photographers captured them in action. Few journalists ventured into the tunnels to write about them. The miners knew their value, but to the outside world they barely existed, and partly because they were victims of their own success. The locomotives were so reliable, so mundane in their operation, that they stopped being newsworthy. They just worked, day after day, year after year. No dramatic failures, no spectacular achievements, just steady, unglamorous utility. By the time diesel and electric locomotives arrived in the early 20th century, the fireless steam engines faded away without ceremony. They'd done their job. Nobody felt the need to preserve them or celebrate them. Today, not a single example survives intact. A few fragmentary pieces exist in mining museums. A wheel here, a pressure gauge there. But the complete locomotives are gone, scrapped for their metal during the World Wars, abandoned in sealed mine tunnels, or simply rusted away in forgotten corners of collieries that closed decades ago. The engineering drawings exist in archives, but the machines themselves have vanished, which raises an uncomfortable question. How many other engineering achievements have we forgotten simply because they worked too well, too quietly, in places we couldn't see? The Queensland underground steam locomotives weren't flashy. They didn't set speed records or win industrial exhibitions. They just solved an impossible problem and kept solving it for decades. In the history of steam power, that might be the most impressive achievement of all.